Alright, this is part one of the lesson on physical science, motion, speed, velocity, and acceleration. There are lots of times during this video that you're going to want to pause. There are papers that go along with it and that you will be filling out as we go. And if a substitute is running this video, then the substitute is going to want to pause at appropriate times to give the students opportunities to work. So here we go. Motion, speed, velocity, and acceleration. First thing we have to think about in this chapter is what is motion. I think that if I asked you all to write down a definition for motion, you would come up with lots of answers that were things like when something is moving. Okay, and that doesn't really define it. You can't define a word by itself. So we're going to first define motion. To observe motion, you first have to observe that object in relation to another object that stays in place. And we call this thing a reference point. So when you talk about something moving, you're actually talking about two things, the moving object and then the reference point, which is your second object. When an object changes position in comparison to a reference point, then we say that object is in motion. Another way to say in comparison is relative. And relative is a really common science word. It gets used a lot. And if you take physics when you're a junior or senior, you'll learn that it's a very important word in physics also. So anyhow, changes position relative to another object, we say the object's in motion. If you really want to talk about motion, you need to know both the distance the object moved and the direction that it moved. And that will allow you to describe the change in position, and that will allow you to describe its motion. Probably seems a lot more complicated than it needs to be, but that's because you're in high school now and it's time to start learning what things really mean. Alright, so let's look at a few questions that have to do with this idea of one thing moving relative to another. So I have over here, I have a train car, and believe it or not, this is a cat and it's asleep on the train car. So there are a couple different questions that we could ask here. One is, we could say, how fast is the train moving relative to the ground? So we're talking about the motion of the train, and our reference object is the ground. And you see right here an arrow. You see, I also see a W and a G. They don't mean anything. You can ignore them. But you see this big old arrow here, and it's pointing this way, and it has a measurement with it. And this measurement is a speed measurement. It says 45 miles per hour. The arrow tells you the direction of the motion. So, how fast is the train moving relative to the ground? 45 miles per hour. Alright, now how about the cat? The cat's asleep on the train. How fast is the cat moving relative to the train? So we're on this question now. How fast is the cat moving relative to the train? 0 miles per hour. Alright, how fast is the cat moving relative to the ground? So now we're interested in the motion of the cat, and our reference object is the ground. And the answer to that is 45 miles per hour. That was an easy one. Alright, now our cat is awake and he's jumped up and he is also running. So he's on the top of the train and he is running at 45 miles per hour. And the train is traveling at 45 miles per hour. Now, eventually the cat, not eventually, pretty quickly, the cat's going to run right off the top of the train. So we're talking about just a short period of time that the cat is running at 45 miles on top of the train, which is also running 45 miles per hour. So our first question is how fast is the train moving relative to the ground? Just like in the last problem, the train is moving at 45 miles per hour. How fast is the cat moving relative to the train? 45 miles per hour. And how fast is the cat moving relative to the ground? So now we're interested in the motion of the cat, and our reference object is the ground. So what do you guys think it is? It is 90 miles per hour. How did I get that? Well, the train was moving 45. The cat was moving 45 miles per hour in the same direction. Wait, how do we know it was the same direction? Well, because the arrows are pointing the same way. So these two numbers are going to get added together. So relative to the ground, the cat's moving 90 miles per hour. Alright, now we got a really similar one, except this time, look, you'll see that the cat is only going 20 miles per hour. And we make this arrow a little bit shorter than it was on the, it should be a little shorter. Okay, it should be a little bit shorter than it was on the previous page to show 20 miles per hour. The train is still moving at 45 miles per hour. The cat and the train are still going the same direction. So how fast is the train moving relative to the ground? Still 45 miles per hour. How fast is the cat moving relative to the train? 20 miles per hour. And how fast is the cat moving relative to the ground? Alright, what do you think? You think about it for a second. And the answer is 65 miles per hour. How did we get that? Well, we added 20 and 45 and we got 65. We added them because they were going the same direction. So if you were standing down here, alright, you're standing down here where the arrow is, and you were looking up and you were watching the train and the cat go by, it would appear to you that the train was going 45 miles per hour. It would appear to you that the cat was going 65 miles per hour. Alright, one more. Now we have the cat running 20 miles per hour, but look at the arrowhead. Alright, now the cat's going the other direction. So it's running towards the back of the train. So question number 1. How fast is the train moving relative to the ground? It's still going 45 miles per hour. And how fast is the cat moving relative to the train? It's going 20 miles per hour. See that negative sign right here? The negative sign indicates direction. So it tells us the cat is going a different direction than the train is going. And how fast is the cat moving relative to the ground? Alright, what do you think? And the answer is 25 miles per hour. How did I get that? Well, the train was going one direction, the cat was going the other, so I took the difference between the two. 45 minus 20 is 25. And you notice there's no negative sign? That's because the cat is moving the same direction overall that the train is going. Alright? So, if you were standing on the ground and you were looking up at the cat, you would see the train would appear to go 45 miles per hour. The cat would only appear to be going, the train would be going 45 miles per hour. The cat would only appear to be going 25 miles per hour, but it would be going the same direction as the cat. Alright, remember, we have to show that the 20 miles per hour of the cat is the other direction, and how do we do that? With a negative sign. Alright, the frame of reference, again, is the object you're comparing to. Sometimes it's called the frame of reference, sometimes it's called the reference object. Very often the reference object is the ground. Well, we're going to be doing a lot of math type problems in this class, and if it ever doesn't say what the reference object is, you can assume it's the ground. So, say you're solving a problem about a horse, and the horse is running, and the question tells you how far it's running and how long it takes to get there, and it asks you the speed. You just assume that the reference object is the ground. Alright, also, all those arrows that we saw in the previous pages were called vectors. So here's a good example of a vector right here. There you go, there's a vector. It would have a number associated with it. We would call that number the magnitude. And it also has a direction. So the length of the arrow should be made longer or shorter, even if it's not exactly. If you just make it a little bit longer and shorter to show different magnitudes, and the direction is pointing. Alright, so if we were calling this arrow 17 meters per second, then if we wanted to show a vector arrow for 15 meters per second, we want to make that just a little bit shorter. If we wanted to show 15 meters per second going in a different direction, we'd have the arrow pointing in the other direction. We use vectors a lot in science. Anytime that we want to talk about a measurement that has amount and direction, we're going to use vectors. But right now, we're just going to use them when we're talking about velocity. Alright, you have, or you should have, a paper that looks like this. So if you don't have this yet, this is a good time to get this passed out. So at top it says home assignment relative motion. We're not going to use it as a home assignment, though we're going to use it as a classroom assignment. So pause if you need to, and everyone get that paper out. First question. Suppose you are riding in a plane at a constant speed and a suitcase is dropped from the plane. Draw a picture of the path of the package with respect to the plane. And number 2, that same object, suitcase, is falling with respect to an observer on Earth. Now we're going to fill this one in for you, so you want to copy this onto your own paper. if you're in the plane and you've dropped a suitcase and you look down, it's going to look like the suitcase is dropping straight down. But if you are watching it on Earth, it's going to look to you like the suitcase is following this path right here. Okay? Now, I told you about 1 minute ago that we are only going to use arrows when we talked about velocity or speed, and I lied because right here I'm not using it for that purpose. I'm using it just to depict motion in general. But very soon we'll start using these arrows to refer to velocity. So here they're just showing the motion. Alright, straight down, if you're on the ground watching it, it will seem to follow a curved path. Well, why is that? Well, that's because that falling object has inertia. Alright, so even while it's falling down, it still is continuing to go forward and showing this path if you're watching it from the Earth. Alright, now you try 3 and 4 yourself on your paper, and pause this long enough for the students to answer these two questions. Alright, number 5 says, draw a vector diagram of a spider crawling along on the floor of a little red wagon. The wagon is moving at 1 meter per second relative to Tommy, a stationary observer, and the spider is traveling at 0.25 meters per second relative to the wagon. So the spider is on the wagon, it's crawling along the wagon. So here's my first vector. This vector right here is showing the velocity or the speed of the wagon itself. And it's going 1 meters per second. Alright, now here is our vector for the spider. So the arrow is going the other way. It's smaller, it's 0.25 meters per second because the spider is traveling along towards the back. Okay. Alright. By the way, if we were telling the story about the spider going in the same direction, we would have the arrow like this. But I'm going to say in this particular story, I'm going to say that the spider is going towards the back. Alright. Now, this is what you copy down onto your paper. Alright, for question number 5. This is vector diagrams. Alright, this is question number 6. What is the speed of the spider relative to Tommy? Draw a vector showing the direction of the spider's motion relative to Tommy. So we started out with these two vectors. Red is the wagon, blue is the spider, and the purple vector is the vector showing the spider's speed relative to the observer. How did I get this? Well, these two are in opposite directions, and we could designate this with a minus sign if we wanted to. And I did just because I showed the arrow, and since they're different directions, we take the difference between them. So what you need to do for the answer for this paper is you need to write down this purple arrow, and then you need to write down what its magnitude is. So write down the number that shows the size of this arrow, which is the speed of the spider relative to Tommy, and then put your units down. So you do that now. You write down the purple vector, and you write down the value that goes with it. Alright, now you're going to put your name on this paper, we're going to turn it in. I'm going to stop this now, and we're going to move on to part 2 when you're ready.